required to write queries. But whenever you request information from the database, the request is essentially a function call. Now this function call is not a remote function call. It's not even RMI, you know, remote method invocation, right? Calling functions from one machine to another machine across the network. Across the network is again TCP. It's not even RMI. It's a local function call because when you deploy code, the only catch is you need to deploy code on the platform. And when you do so, the database actually merges into your code to expose functions directly to you. So it is data storage truly built into any Java EE platform. Right? And we thought that made sense. Now you'll say, why is that required? Correct? What's wrong with the current approach? Correct? Now, there is the main thing. There's a reason why it is done that way. Let's say you are having a big data application, right? And your big data application, you fire a query. The query returns a 100 MB response set. Fair enough, right? Billions of records, you fire a search query, that search query matches a million records, the million records come to 100 MB in size. A pretty reasonable estimate, right? What's going to happen in the old way is that you are going to consume 100 MB of virtual memory on the database for your query result. Then you're going to pass this data onto your application, consume 100 MB of virtual memory, which is RAM, on your application again, right, to process this data. So what you're doing is basically essentially consuming 200 MB of virtual memory when you actually needed just 100. Everyone knows RAM is expensive, right? You don't have all the RAM in the world. The more you save, the better your servers perform, correct? There's additional implications to this. When you're passing data over a TCP channel, you have to marshal and unmarshal that information, right? Marshalling and unmarshalling means you have to encode the information, right, on the database end. You have to encode it to TCP compliant protocol, transport it to your application. Application needs to decode it, correct? Now that takes significant amount of CPU. Now till the time you are using this in relational models, the amount of time it took to encode and decode and the amount of RAM it consumed wasn't relevant because your search queries resulted in hardly 1 KB, 2 KB, 4 KB responses. But big data, it matters a lot because the data size is huge, the time to encode and decode is huge, and the amount of RAM it consumes on two ends is completely unjustifiable, right? So you combine these two, you get a tremendous performance boost. Now comes the question, how much performance boost? Right? Okay, we understand, we save RAM, right? We're saving CPU, fine. What is the gain? Let's talk statistics, right? What is the gain? You all want to know? Yes? So this is what Blob City is, and that is what no query is, basically, removing the architecture. Okay? So coming to the performance, I'm not sure if the last people can read this. It's 600 operations per second. Okay, that's what is written at the bottom. So what we did is, let's say you're using Blob City with yes query. Yes query means the old model over TCP channels. We do support it. We fully support it. We have support for JDBC. We have support for ODBC. Okay, there is nothing that's not supported. It's fully backward compatible, but gone one layer ahead for customers who really want to leverage the no query performance. They can leverage it, right? So what do we do exactly, right? So it's basically load tested on a single machine, right? With, say, I think it was 10 million records. I don't know how many records it was. It doesn't really matter, the amount of records. And we have tested it from 0 threads to 500 threads. So you're testing from one concurrent session, basically, up to 500 concurrent sessions hitting the database for transactions, right? Now when we try this through yes query, that is over TCP channels, we got 600 operations per second. Now we did exactly the same thing on the same hardware, same machine, same config, same data, everything same. Only this time we did not use the TCP. We used Blob City in no query mode, right? What happens? This is what we get. That's 2,000 operations per second. 233% rise in performance. Significant? Significant? Yes? What did we do? We just removed one TCP layer. Right now, it was possible for us to remove that layer. There are still other layers that are existent. Right? Now, imagine what happens if we remove the TCP channels. Now, there isn't technology available to remove all TCP layers, right? So we just optimize what was technically possible with what we have today, right? Tomorrow, we may be able to come with a better protocol, remove more TCP layers, and gain far better performance than what we get today. But the key thing to note from this is when we are designing systems, right, we have to keep in mind how many blocks we are actually putting together. The more the blocks we put, the lesser the total performance you get, right? And nobody ever tried this. I'm sure some of them have tried it. But in general, this is the stats of what's the implication of putting that one extra communication block in a system. And I'm pretty sure it's pretty consistent with other blocks as well, right? So moving on further, this brings me to my second part of the whole presentation. So that was basically no query at its best, right? Giving you what type of performance boost. Some things that go on from now on may be specific to what Blobcity offers, okay? And this I want to talk about in terms of what we actually lost, right, when we moved from SQL to NoSQL, and what we don't have today and what we need, correct? So SQL systems are widely used even today. Probably we have been using them for the last 40 years or so, right? We had a lot of features. We had transactions, we had relational data models, we had stored procedures, right? A lot of them. We moved to NoSQL because we needed horizontal scalability, not vertical scalability, right? Our hardware was peaking. We could not go vertical scalability. That was not the way. We needed horizontal scalability. So when we built NoSQL, what we did is we actually lost a lot of features that were in SQL. Some of them are transactions, right? Relational data models. They don't exist in NoSQL, right? Stored procedures. There's no way you can run any piece of code within a NoSQL database, right? It's completely lost, correct? Why? Because we wanted horizontal scalability. But let me ask you a question, okay? We have cracked one part of the problem, that's processing huge amount of data with NoSQL. It's pretty much possible. You use Hadoop, you use HBase, Cassandra, MongoDB, anything. It's pretty much possible, right? But let me ask you a question. Have we solved the other part of the problem? Our production systems are still on SQL, right? How many of you have actually faced a problem because of lack of relational database performance? How many? Quite a few? Okay, I see some hands going up, right? I'm one of them. Okay, I do a lot of consulting for multinationals, and I've seen this happen quite frequently, right? But what's the solution? Does anyone know a solution for this? Anyone? Sorry? Data sharding, right? But SQL systems, by virtue of the data storage mechanism, don't allow sharding. Right? That's the reason the relational systems are not. It's kind of done the right way. Okay, the relational systems were built the right way. They were built the right way 40 years ago. But at that time, what seemed to be huge data is nothing today. Right? The whole design that we did so many years ago has failed because we never anticipated data could grow so large. It's just unimaginable. But today, that unimaginable has become true. Right? It's so much information. I know companies who generate 30 terabytes of log files per year for just web logs. That's the amount of logs user activity generates. And let me tell you, that's still not the biggest of biggest deployments. 30 terabytes will be small for quite a few over here, right, in terms of web logs. But how do you process that, right? You want to process it, correct? So what you're trying to aim for is basically give you all the features, okay, that SQL offers. That's what Blobcity is doing. It's allowing you to use all the features of SQL, have transaction support, have relational data models, connect with the traditional ODBC and JDBC protocols, run your SQL queries. We are fully SQL 2003 syntax compatible, right? And giving you the ability basically to scale up your production environment for live data by replacing your relational databases with Blobcity solution, which is a big data solution. Now, Blobcity follows, okay, a flat file storage. It doesn't follow the relational storage. That's how we can give you significant performance. It has everything from sharding to data replication to failover management, everything that you can imagine for horizontal scalability. From a scalability point of view, you're never limited, right? Because you're following in the NoSQL category of databases, if you feel that your system is not performing, what do you have to do? Can anyone answer? What do you have to do? Anyone? No, we are having this conversation because relational databases are not performing, right? So when relational performs, you put Blobcity in, you have a distributed architecture with all the relational support, and then Blobcity doesn't scale up. What do you do? The deployment of Blobcity doesn't scale up. What do you do? For relational, what do you do? I look at the code. Relational doesn't scale up. I look at the code. I look at the software architecture. But when a system like NoSQL or a distributed environment doesn't scale up, what do you do? Anyone? Keep expanding, right? Just keep adding a node. You don't get performance, add one more node. Falling short, one more node. Falling short, one more node. Never ends. Just keep adding, it's going to keep scaling up. Right? Now, here's the catch, okay? Before I go ahead, here's the catch. I was having a conversation once with my architect. He's here apparently, Karun, sitting on our desk, right? And he came to me and he said that he tried this particular sample with a NoSQL database. Let's say arbitrary figures, okay? He says, I tried it one instance, right? And I got 100 operations per second performance. Okay, now I took the same data, say 100 million records, I took the same data, and I added one more node in parallel. Okay, this time what happened? Each node gave 120 operations per second performance. Following? I said that doesn't make sense. If one node caps at 100 operations per second maximum performance, how can the existence of one more node increase the performance of the first node? Does everyone know that this is true for a fact? Everyone know this, right? Why is it? Do you know why? Because every system has a rate of degradation, right? If I'm putting 100 million records on one server, it degrades. The performance of the database on the 100 millionth record is less. But when I have two servers, and let's say you split data equally, each server this time gets 50 million records. Now the performance of each node at a 50 million record point is far better than their own performance at 100 million point. Right? So now, apparently, instead of giving 100 operations per second, idealistically, I would have expected one node 100 ops, two nodes 200 ops. No. What happens? Two nodes 240 ops. Because both perform far better because both have less data. Right? So the more the nodes you add in a cluster, the more the system scales. So the least you have to ever worry with any NoSQL solution, not necessarily just ours, any NoSQL solution is scalability. That's the least of your problems. Right? So let me get to some key things and explain these features, okay, that we offer. So this was the SQL trend. Right? As data kept on increasing, the performance kept on decreasing. That's why we have come to the concept of data sharding, replication for failure management, okay, and gaining performance by distributing the data, right? Across nodes, you gain in performance. But, okay, so here are some of the features that I would like to tell you. Features that Blobcity gives you is superior indexing. Okay, what superior indexing does is it's any indexing that you're familiar with SQL systems. B-tree indexes, hashed, unique indexes, everyone has heard? Almost everyone has heard, right? So we give you all those indexes, okay, in a distributed environment, distributed fashion, right? We give you triggers. Triggers basically run on DML operations, okay? That's whenever you're doing an insert, update, delete, a trigger is invoked. A trigger can perform changes, right, on other tables or itself by a rule set that's programmed into the trigger. Trigger is nothing but pieces of code. They can virtually do anything, and they run within the database, right? So what the trigger can also do, one of the features what the trigger can achieve is mimic relationships. Wherever you have a foreign key in your SQL deployment, we replace them with triggers in Blob City. And the trigger can ensure the foreign key constraint. So you can take table 1, always insert in table 2. Okay, with a precondition that this condition has to match. That's what a relation is, right? And the trigger allows you to mimic them. So you got a whole relational data model in a distributed architecture. Correct? Then you come to filters. Filters are basically used for search operations. So when you're reading data, you're running a filter, right? It's only for selects. But what we do is we allow you to have code running within the database, right? Powerful code, it's Java or Scala, you get two choices. People familiar with object-oriented programming will choose Java. People familiar with functional programming, which is a different paradigm altogether, would choose Scala, right? And you can write code in these two languages, run it within the database, and have it perform scan jobs, full scan jobs at a real fast speed without actually picking up the data. You perform it within the database. It's like, to give you an example, for analytics, most likely you will do a pattern search, right? Now, even if you're using something like Hadoop and you want to do a pattern search, Hadoop is different. Hadoop is used for batch processing. It's not used for real-time data, right? We're talking about real-time data here. But if you were to do a pattern search, say comparatively real-time meaning edge-based or something, right? You would basically pull all the records, search for a specific pattern, and then give you a result. Selecting all records will take a lot of time. What you want is the ability to run a pattern search within the database, right? Wherein the database itself has smart logic of eliminating false points that do not match your criteria. It speeds up significantly. So you write your logic in a filter, run the filter on the database. The filter gets the whole result. It has an accumulator. It accumulates the result, gives you a full response set that matches the search criteria. Consistency and everything is always ensured. Okay, so you will not get false positives. Okay, that will never happen. The next is transactions. That's the main thing, right? Transactions is what makes SQL databases usable, right, in your live systems. That's what you want. You don't want your data to get, if you basically a transaction fails or any error occurs, you want the system to roll back. You don't want stale information. You don't want incorrect values being persisted in your database, right? Blob City is fully transaction supported. Okay, all asset properties are ensured in a distributed environment, including to the extent that even triggers are transacted. So when a trigger mimics a relationship and the trigger fails to execute that relationship because of some error, the whole operation, the whole mutation operation that you performed, insert, delete, modify, anything, will all get reverted. Right? And that is what is a transaction, right? And we give you all of that. Correct? So, coming to the key point, right? We all want to know, okay, this is there, right? We have all these things. But how does this software actually compare with other solutions out there? Everyone wants to know, right? How does it compare? So let's go to this, right? We did a comparison for a read-only test. Read-only, why read-only? Because many of us basically use big data solutions for analytics. Analytics is mainly read operations, right? Lots of read operations. So it's a read-only stats. I can share the whole statistics with you later if you want for all types of workloads. That's possible. So what I have here is the read-only stats. So we tried the statistics is performed using YCSB. That's Yahoo Cloud Server Benchmarking Tool, okay, which is a database benchmarking tool provided by Yahoo. We tried it on MongoDB and we tried it on Cassandra. This test was carried out for 100 million records on a single node. Okay, why single node? Because we want to show how much, by what percentage, does our database perform better or lesser, right, than these databases on a single node. When we put it in the cluster, we obviously know it's going to perform far better or far lesser, right, by the same percentage. Actually, much more. It just goes in a logarithmic form. It's not linear, right? So Cassandra was giving us for 100 million records in the table, 10K size per record.